As we consider the preparation of aldehydes and ketones, we should recognize that Mother Nature is a really good synthetic organic chemist, and there are a lot of naturally occurring aldehydes and ketones. Here we have just a few examples. The first one is vanillin, and we can see that this is an aldehyde, and this is a major component of vanilla extract. Next, we have cinnamaldehyde, another aldehyde, and this is a major component in cinnamon. Citronellal, yet another aldehyde, and this is what we find in citronella candles that help keep mosquitoes away. And our last example is called camphor, and this is a ketone that is a component of many itch remedies. So one of the common features of many aldehydes and ketones is that they do have an odor. Some of them are quite pleasant, some of them not so much, especially if you are a mosquito. A very useful way to prepare aldehydes and ketones is by the oxidation of alcohols. If we have, for example, a primary alcohol and we oxidize this with sodium dichromate and sulfuric acid, keep in mind this is a source of chromic acid. Well, this actually is going to oxidize all the way up to a carboxylic acid. In other words, this isn't a way to make aldehydes or ketones. However, there are a number of reagents that have been developed that can convert a primary alcohol to an aldehyde without over-oxidizing to the carboxylic acid. So one example is PCC, or pyridinium chlorochromate. We also have the Des-Martin periodinane. We can use bleach with tempo, which is a catalyst. We can use the Swern oxidation, which uses DMSO, dimethyl sulfoxide, as the oxidizing agent. So these are just a number of reagents that can be used to convert a primary alcohol to an aldehyde. If we have a secondary alcohol, this one can be oxidized by chromic acid, usually prepared in situ by combining sodium dichromate or potassium dichromate with sulfuric acid. And in this case, we are going to make a ketone. If we use one of the specialized reagents, such as PCC or Des-Martin, bleach, Swern, any of these will give the same product as the one we get from chromic acid oxidation. So we can carry out a functional group interconversion, converting an alcohol to an aldehyde or to a ketone, depending on the original structure of the alcohol. And there are a number of different reagents that can be used. So oxidation of alcohols is a very common way to access aldehydes and ketones. Another way that we can access ketones is by carrying out Friedel-Crafts acylation. So rather than just doing a functional group interconversion, here we are actually making carbon-carbon bonds to give us an aryl ketone. So Friedel-Crafts acylation is an example of electrophilic aromatic substitution, and commonly we have an acid chloride and we combine that with a Lewis acid aluminum trichloride. When we carry out an acylation, remember it is this acyl group that becomes connected to the aromatic ring. So treatment of benzene with acetyl chloride and aluminum trichloride will result in the formation of this aryl alkyl ketone, and this one is called acetophenone. In our next example, we have a different acid chloride. We're still reacting it along with aluminum trichloride, but this time we're starting out with a substituted benzene. So there are a few things we need to keep in mind when we are trying to carry out a Friedel-Crafts acylation on a substituted ring. One thing to consider is the acid chloride. And so remember that this is the piece that is going to become connected to the benzene. Another thing we have to focus on then is the substituent that's already present on the ring. With an ether, this is an electron releasing group, which means that the ring is activated, and this reaction will happen faster than if we were to carry out the same reaction on benzene. But furthermore, it is an ortho-para director. So that means that this group is going to be installed ortho or para to the methoxy group. So from this reaction, we should make this product along with some of the ortho. Because this is pretty big, I would guess that we're going to get more para than ortho, but we should consider the formation of both. In our last example, we are again trying to carry out a Friedel-Crafts acylation on a substituted benzene. So looking first at the reaction conditions, we have an acid chloride, and this is the group that we're trying to substitute onto the ring. And if we look at the substituent that's already present on the ring, we know that NO2 is an electron withdrawing group. No matter what the nitro group is connected to, we can always think of it as an electron withdrawing group. In the context of electrophilic aromatic substitution, the nitro group is a deactivator. In fact, it is very, very strongly deactivating, which means if we try to carry out a Friedel-Crafts acylation, we are going to get no reaction. So recall, Friedel-Crafts alkylation or Friedel-Crafts acylation can occur on benzene substituted with electron releasing groups, which are activators, or benzene substituted with halogens that are only weakly deactivating, but they cannot be carried out on a ring that is strongly deactivated. Despite having some limitations, we can see that the Friedel-Crafts acylation is a way to access aryl alkyl ketones or aryl-aryl ketones.